Welcome to my video lecture on hypothesis testing procedure for the difference of two proportions. Now, in this test, we go through the same thing whether you have one population or two populations. Your hypothesis testing procedure will remain the same, which means you set up your null, your alternative, then you calculate that numerical value known as the test statistics, then you use your distributions to construct the rejection region, and then you ultimately determine if that test statistics has fallen in the rejection region for you to reject, or has it fallen outside the rejection region in which you will fail to reject. So the overall four-step procedure for hypothesis testing does not change whether you're testing one variable or the comparative testing of two variables. So these are also called comparative testing or the test of significant difference, because when you're testing the difference between two variables, you're not trying to test the value of each one, you're trying to test the value of the difference. So basically all you're doing is trying to find out if there's a difference between the two percentages or not. And in the test of two population in hypothesis testing, that's basically all you could prove. Your business is not a lot with the alternative. Your business in the test of two populations is always with the null hypothesis, and you don't really, the conclusion and the decision are both geared toward the null hypothesis. In one population testing, recall that the rejection, the failure to reject, which is the decision part, is always towards the null hypothesis. And the conclusion is sometimes depends on the original claim. In two population, both decision and conclusions are geared toward the null hypothesis, independent of which one is the original claim. Just remember that, and you'll see it in the conclusions. So here, the only thing new I like to mention before I give you an example is that you'll see in the test statistics, guys, you've seen P1 hat, you've seen P2 hat, you've also seen Q1 hat and Q2 hat, but don't exist here. You don't need them, but you see a new variable called P bar and Q bar. I don't want you to panic about that. I've told you what P bar is, and remember, usually in stats, every time you see a bar on top of a variable, it just means average. So it's almost like a weighted average. If you have two x's and two n's, the sample percentage for the both of them is calculated using the formula x1 plus x2. You add the x's and you divide it by the sum of the sample sizes, sum of the n's. And of course, Q hat's always 1 minus P hat. So that's the only new thing you're going to encounter. And remember that we're always in the test of hypotheses for two population variables, in this case proportions. We always start with the fundamental assumption that the difference between the two is zero. So we want to believe that the two populations we are testing have the same percentages of whatever it is we're trying to test. So we always start with the status quo that says the difference is zero and we're trying to reject it or fail to reject it. So we're always assuming there's no difference, and then we want, as a test person, as a person that's doing the test, as the researcher, to reject that statement. And we're going to have to see if we could or could not do so. Let's start looking at an exercise here. So I have 50 stats professors from Los Angeles. 8 of them use technology to teach stats. We have 90 such professors in New York. 12 of them indicated they use technology to teach stats. And the question is, using a 5% significance level, we're trying to test the claim that whether the proportion of professors using technology in Los Angeles is greater than the percentage of professors using technology in New York. So you're basically trying to prove that the percentage of professors in LA that are using technology is greater than the percentage of professors in New York that are using technology. Now remember, the status quo here is that there are, very good, they're the same. Or if you want to even go with the opposing statement, it'll be less than or equal to, but remember, we only preserve the equality because for the null hypothesis, you have to have a singular value written for the mathematics to make sense. Okay, so that becomes my setup for the null and alternative, and I'll take it from there. So I have it typed up for us to see it. So there we go, and I had it for you. So that's my claim, and again, it doesn't matter because the conclusion and the decision are both going to be geared towards the null hypothesis anyways. So I'll write my claim, which is the strict inequality with the alternative, and I write P1 equals P2 for the null hypothesis. And I always write down the given information in a table. especially when I'm dealing with two populations, because a lot of numbers will be going around. Now, the second step of a hypothesis testing procedure, as I've told you, is to calculate the so-called test statistics. Let me write you the test statistics for two population proportions. You don't need to remember this because you're going to have this on your formula sheet, but I'm just going to write it for you. Here we go. Remember, it'll be P bar Q bar over N1 plus P bar Q bar over N2. These are a lot of calculations and a lot of decimal values. So you definitely do not want to do this with paper and pencil. Because remember, what you need to do is you need to find P1 hat, which is, 8 divided by 50. You need to find P2 hat, which comes from here, which is 12 divided by 90. Then you need to find P bar, which is x1 plus x2 divided by n1 plus n2. And then you want to find Q bar, which is 1 minus P bar. And that's just a lot. And then once you do that, then you have to take all that and type it in there. And remember, the hypothesized difference we're assumed to be 0 because of that. And then we'll see if we could reject it or not. And this is always the case. Alright, so again, this is something totally done on a spreadsheet. So I'm going to try to do this with you on a spreadsheet. Let's see if we can pull this off. So we can copy that. Now I'm trying to calculate the test statistics here, and I'm going to type that on Excel for you guys to see it. So let me proceed to my spreadsheet here. There we go. And I'm gonna let's see, insert. Where is my formula? Oh, there we go. Oh, doesn't want to come in, so let me delete that, I guess. So I know what the values are. So I'm actually gonna write down the values for you guys here, and hopefully I can erase these little dots here. Very good. So let me start typing my values here. Yeah, Excel sometimes doesn't want to cooperate with us, so we're just going to start from scratch. So what are my values? If you don't recall, you could always look at that. X1 is 8, 50, 12, and 90. So my x1 is 8, my n1 is 50, my x2 is, what is it guys? 12 and 90, very good. So x2 is 12 and n2 is 90. Alright, so we need to find P1 hat, we need to find P2 hat, we need to find P bar, we need to find Q bar, and once I have that, then I can calculate my test statistics. I'm going to try to copy this one more time because it's very important for us to see the test statistics and how it's calculated. So let me cut that, and hopefully I can bring it in here, so copy it. Let me go back to my spreadsheet. No, can't do it. That's fine. I don't particularly like spreadsheet on an iPad, but that's okay. And I'm making it a little bigger for you guys, and I'm centering everything so you can see how. And let me increase the font size so it's a bit bigger. There we go. So how do I calculate my P1 hat? P1 hat is x1 divided by n1. My P2 hat is x2 divided by n2. My P bar is x1 plus x2 divided by n1 plus n2. Easily done on a spreadsheet. Don't forget the parentheses in the numerator and denominator. And my Q bar is 1 minus P bar. Okay, so now I'm ready to calculate the test statistics, which is P1 hat minus P2 hat minus 0, but we don't need to write that, divided by the square root of P bar times Q bar divided by n1 plus p bar times q bar divided by n2. And that's how I would type my test statistics, which is 0.432. So you could always look at that with the video and rewind it. So my test statistics is 0.4 almost. So if I go back to my problem, and I've shown you how the computations here manually, but you never do that manually. So here is the thing in a nutshell. So you write your null and alternative hypotheses, step 1. You write your test statistics that you calculated on Excel as step 2. Again, you look at the direction of the inequality in the alternative hypotheses, and you notice that it's pointing to the right. So it's going to be a right tail test, and only one. Alpha here, let's look at the exercise. Alpha is given, it's 0.05. So if I go back to my problem, since alpha is 0.05, and it's a z test, always when you're testing p, it's a z test. So in order to calculate that numerical value, I need to look at the area to the left. If that's 0.05, then the area on the left is 0.95. And if I type my norm dot s dot inverse of 0.95, then you will read 1.645. So that's how you know where the rejection region starts from, almost the gatekeeper. Now, that number is 0.4, this is 0, so therefore my test statistics fall somewhere in the fail to reject or in the non-rejection region. So my decision will be fail to reject the null hypotheses. So you're failing to reject the fact that they're equal. So if you're failing to reject the fact that they're equal, that means they are indeed equal. So, but you can't say that. So the proper statistical conclusion will be, remember, you have statistically proven that there's not much difference there. And that's what you got to say. There doesn't seem to be a significant difference between the percentages. You can't say they're equal. So you say you just, because remember, we always want to go with the whole foundational concept of hypothesis testing is to always, for the researcher, go in the direction of trying to reject the null hypotheses. Because in practice, the null hypothesis is always the status quo. And a researcher, why would you want to do a research? Well, because you always want to go against the status quo. Because if you agree with the status quo, then why are you even doing the research? Just let it go. So the idea is always to try to reject the null hypotheses. And that's how the conclusion has to be geared to. So you either say you reject it, it's no good, or I couldn't reject it, and I couldn't find enough evidence to reject it. Okay, and that will be my lecture on the hypothesis testing procedure for two proportions. See you guys on the next test.